Hi, welcome back. Today we will be solving physics high level paper 2. It's going to be November 2016, time zone 0, and it's going to be 2 hours and 15 minutes long paper, and calculators are allowed. Okay, so let's get started. Question number 1. A tennis ball is hit with a racket from a point 1.5 meter above the floor. Okay, so the height of the person is 1.5 meter above the floor. The ceiling is 8 meters above the floor. The initial velocity of the ball is 15 meters per second at 50 degrees above the horizontal surface. Okay. Assuming that air resistance is negligible, so there is no air resistance occurring here. Okay. Determine whether the ball will hit the ceiling. Okay, so the distance between the ball and the ceiling, this much. Let's see how much is this. This is the distance between the ceiling and the ball. So you can see the total distance between the ceiling and the floor is 8 minus this length. So 8 minus 1.5, which is 6.5 centimeter. So this is the available distance that the ball can travel. And if the ball travels a vertical distance longer than 6.5 centimeter, it's not centimeter, sorry, it's meter. Everything is in meters, so ignore. Ignore centimeter here. Everything is in meter, meter, meter. So the available distance to us is 6.5 meter. So if the vertical distance traveled by the ball is bigger than 6.5 meter, it means this is only possible if the ball hits the ceiling. So determine whether the ball will hit the ceiling. So first of all, we need to know what is the vertical velocity, because we're only interested in the vertical displacement, vertical distance traveled by the ball. And if the vertical distance traveled by the ball at the maximum height, at the maximum possible height, is bigger than 6.5, it means it is going to hit the ceiling. Okay, so the first step that you need to do is you need to resolve this 15 meter per second into two components. So apply the Sokotowa rule. So you can always divide this resultant velocity into two parts. So this resultant velocity can be divided into horizontal component and vertical component by this right angle triangle. Okay, so this is our angle theta. So if you still remember the Sokotowa rule, so when you have a right angle triangle, so for example like this, so this is the right angle, this is the angle theta. This length, the length opposite to the angle is opposite. This one is adjacent, and the length side opposite to the right angle is called the hypotenuse. Okay, this is from the right angle triangle. So sine theta is opposite over hypotenuse, and cos theta is adjacent over hypotenuse, right? And then you also have tan theta, which is opposite over adjacent. So these are the three Sokotowa rules of a right angle triangle that you should remember. Okay, so if you consider this triangle, this is hypotenuse opposite. Opposite over hypotenuse is sine theta. So this vertical velocity will be 15 times sine of angle. Whereas the horizontal component of the velocity will be hypotenuse opposite adjacent. So adjacent over hypotenuse is cosine theta. So the horizontal component will be 15 cos of 50 degrees. Okay, so let me elaborate this thing more. So you have a ball here, and this ball has a resultant velocity of 15 meter per second. This resultant velocity can be resolved into two components, which is the vertical component and the horizontal component. The horizontal component that we just calculated is 15 cos of 50 degree, and the vertical component is 15 sine of 15 degree. Okay, so this one is the vertical component and this one is the horizontal component. So we are only interested in the vertical component of the velocity. So here we have the vertical component of the velocity. So the initial vertical velocity, this one, is, call it u. So our u is 15 sine of 50 degree. So you can see this ball travels at maximum possible height some way. So at the maximum possible height, you can see the ball takes a turn, right? So it doesn't go vertically anymore at the maximum possible height. It means the final velocity at the maximum possible achievable height is 0. You need to understand this concept because at the maximum height, the ball is no longer moving vertically. So you can see the ball moves like a projectile motion, and then at the time when it reaches the maximum possible height, it is moving horizontally. No vertical motion is there, and then it goes down. So at maximum possible, so maybe you can write it down here. So at height maximum, your final vertical velocity is 0. Okay, so we have initial vertical velocity, we have final vertical velocity. So at this maximum possible height, we need to find how much is the height achieved. Okay, so since it's a Subag equation problem, because there is a constant deceleration acting in the downward direction, which is like negative 9.81 meter per second squared. Why is it negative? Because it's acting downward. It is opposing the direction of motion. Direction of motion is upward, and the acceleration of free fall is acting downward. So it's opposing the velocity. It is decelerating. Okay, so think of a Subag equation that can be useful here. Why Subag equation? Because there is a constant acceleration or deceleration involved there. So you can see out of all of these four, we will try to avoid the Subag equation that has time in it, because we don't have any time information. We only have initial velocity, final velocity, the acceleration of free fall, and we need to find the displacement traveled. And the displacement moved here is the vertical distance traveled, which actually becomes the maximum height. So ignore the first one because it has time, ignore the second one, ignore the fourth one, use the third one because it does not have any time information, and that is what we need. We don't know what is the time, and we don't want the time to be there in the equation. So we're going to pick the third one. So the reason why we're using Subag equation is because there is a constant acceleration involved there. If there was no acceleration, if the body was moving at constant speed, you will just use speed equals to distance over time. Okay, so let's copy that equation here. So b squared equals to u squared plus 2as. Remember, everything here is in vertical direction. So this displacement is in vertical, this initial velocity is vertical initial velocity, this final velocity is also vertical, okay? And this acceleration is also vertical. So this arrow means these are all vector quantity. Acceleration is also a vector quantity, it's acting downwards, so it has to be negative. Okay, now from our situation, we know this final vertical velocity will be 0. So before inputting any values, what do we want? We want s. We want the height, the maximum height traveled. So make s the subject. So if you make x the subject, you can move this u to the other side, becomes v squared minus u squared, and then divide by 2a. Okay, now let's just input the values into it. The final vertical velocity achieved at the maximum possible height is 0. And the initial vertical velocity is 15 sine 50. Yeah, it's the vertical component of the result velocity. So it's going to be 15 sine of 50 degree. Take the whole square and then divide by 2 times a. So a is negative 9.81. Okay, now just hit the calculator. So in your calculator, just put down this value. And when you just make sure that you take care of the brackets and everything. When you do that, you will get the answer, which will be equals to 6.7 meter. Okay. Okay. Let me help you put down the value in the calculator to make sure that everything goes according to the plan. So you can see this negative just cancel out each other. So we will have a bracket open, 15. We are dealing with degrees, so 15 sine of 50 degree whole square divided by bracket 2 times 9.81, bracket close. Alright, you can see the two negative signs just cancel out each other. If they enter, we get 6.729. So you have to round up to 3 significant figures, so it will be like 6.73 meter. Okay, 6.73 meter. Actually, we have to choose two significant figure here. The reason is because you can see the maximum significant figure that we have in our question is 2. You can see this: two significant figure, one significant figure. So the maximum possible significant figure that we have is 2. We cannot exceed that, so we will have to round up to 2 significant figures. So if we do that, it will be 6.7 meter. So don't exceed the maximum possible significant figure given in the question. In the question we have 2 significant figures at most, so don't exceed that. So the maximum height that can be achieved by the ball is 6.7 meter, but as we know, the available height to the ball is 6.5 meter. So since 6.7 meter is bigger than 6.5 meter, the available height, it means the ball definitely has to hit the ceiling before it can travel an extra distance. So it's like it's going to hit the ceiling and then it will travel the extra distance, so that this total distance becomes 6.7 meters. So yes, it will hit the ball. Yes, it will hit the ceiling because of this. 6.7 meter is bigger than 6. Okay. All right. Question number 2, part B. The tennis ball was stationary before being hit. It has a mass of this much kg and was in contact with the racket for 23 milliseconds. Calculate the mean force exerted by the racket on the ball. So imagine there was a ball here, and initial velocity of the ball was 0. Right? The ball wasn't moving initially, and the ball has some mass of m. And then afterwards, the ball gets hit by a racket. So this is a racket. Somebody's holding the racket, so the racket exerts a force on the ball, and the ball gains some final velocity. In our case, the final velocity that the ball gains is 15 meters per second. How do we know that? As you can see here, so it gains a velocity of 15 meters per second at an angle of 50 degrees, but we can just ignore the angle here. Imagine that everything is like inclined already at 15 meters per second. So I've drawn everything horizontally just for easy calculation. Okay. Yeah, so it has a mass of that. Mean force. So, right, you need to go back to the data booklet, and we will use this equation. This one. The mean force, the resultant force acting on the ball, is equal to change in momentum over change in time, or in other words, rate of change of momentum. So let's use this equation here. So we have the resultant mean force acting on the ball is rate of change of momentum, so delta P over delta T, and you know that momentum is equal to mass times velocity. Change in momentum is due to change in velocity, right? So it's mass times change in velocity. So change in velocity is as a result of final velocity minus initial velocity, and also remember that velocity is a vector quantity. In our case, the initial velocity is 0. So we can replace this one with 0. So as a result, what we will get mass times final velocity. You see, because this part becomes 0, expand the bracket, mass times final velocity is equal to change in momentum. Then we can substitute this mv into here. We will get m final velocity divided by duration of the impact. Now, just plug in the values. What is the mass of the ball? The mass of the ball is this much. So it's 5.8 times 10 to the power negative 2 kg. Make sure it's an SI unit. Final velocity of the ball is 15 divided by delta t. Delta t is the impact duration, the duration of the impact, which is 23 milliseconds, the duration during which the racket is exerting a force on the mass. So it's 23 milliseconds. So you have to convert milliseconds into seconds, which is the SI unit. So multiply by 10 to the power negative 3. Okay, everything is an SI unit. So now just hit the calculator. On the calculator, and just press this time this bracket. Make sure that you have all these brackets, and then divide by 23 in this bracket. Okay. Now if you hit the calculator, you will get an answer of 37.8 Newton because it's a force. So 37.8 Newton. Okay, 37.8 Newton to 3 significant figure or 2 significant figure, doesn't matter. Yeah, 27. So it's a Newton because it's a force. I will suggest just round up to 2 significant figure because we don't want to exceed the maximum possible significant figure. So the maximum significant figure that we have in the question is 2 significant figure, 2 significant figure. So I suggest not to exceed that one. So there's a 37 Newton of mean force acting on the ball. Okay. Explain how Newton's third law applies when the racket hits the tennis ball. So this one is pretty easy. So Newton's third law is applied in all types of situations. Just say that Newton's third law is, by the way, says that for every action there is equal and opposite reaction. So when the racket exerts force, so when this racket exerts force on this mass, the mass will exert an equal but opposite force on the racket. So that is what you need to just explain. Let's look what the maxim says. Yes, the force of the ball on the racket is equal to force of racket on the ball, or you can just include the value there, 38, which was calculated from the previous part, and the ball exerts force in the opposite direction. So make sure you include these two keywords, so it's equal in magnitude and opposite in direction on each other. So racket and ball exert equal and opposite force on each other. Okay, 2 marks. Question number 2. Curling is a game played on a horizontal ice surface. A player pushes a large smooth stone across the ice for several seconds and then releases it. The stone moves until friction brings it to rest. The graph shows the variation of speed of the stone with time. So if you have a speed time graph here, as you can see for the initial 3.5 second, the body is accelerating at a constant rate, then it gets to the maximum velocity. From there onward, probably friction starts to hit and the body starts to decelerate at a constant rate until the final velocity becomes 0. Now before doing this question, you need to remember that, for example, if you have a graph of displacement versus time, velocity versus time, and acceleration versus time, in order to go from displacement versus time to velocity time graph, and from velocity time graph to acceleration, you need to find the slope of the graph. So the gradient or the slope or the derivative of the graph gives you these quantities. So if you have a displacement time graph, you want velocity, and from velocity to acceleration, going forward means finding the slope, and vice versa, going in the opposite direction means finding the area under the graph. Okay, area under the graph, or in other words, integration. Integrate acceleration time graph will give you velocity, and area under the velocity time graph gives you displacement. Okay, so here we have a speed versus time graph. The total distance traveled by the stone in 17.5 seconds is 29.8. Alright, so if you see this chain rule problem, we have a velocity time graph and we are given displacement. So we actually are following this path. So because you can see we are given the distance, and from a speed time graph, if you want to find distance, you have to go in the reverse direction by finding the area under the graph. So in other words, he has already told us that this total area, which represents the distance, is actually 29.8 meter. Okay, so how do you find the area of this triangle? Well, the area of this triangle is pretty simple. It's just half this. This is the base times the height. Determine the maximum speed v of the stone. So we need to find this maximum speed from 0. Okay, so use this concept. The area under the graph represents the total distance, which is actually equals to 29.8 meter, which is found by using the formula for the area of a triangle, which is half base times height. Okay, so let's make it more nicer. Half half base times height. Okay, now because you know that this height can be replaced by this v, because this represents v, which is just equals to height, same thing. So just v, so we have 29.8 equals to half b times v. Make v the subject, so if you make v the subject, it will be v equals to 2 can go up there, 2 times 29.8 and then divided by v. Sorry, b. So just make v the subject. Now plug in the values, so it's 2 times 29.8 divided by b. B is the base, and our base is 70.5 seconds. So just put 17.5 there, and just hit the calculator. So if you hit the calculator, the answer will be around 3.41 meter per second. Okay, corrected 3 significant figure, 3.41 meter per second. So why 3 significant figure? Because you can see the maximum given significant figure is 3, so we cannot exceed 3 significant figure here. Okay, that's the maximum possible speed that can be achieved by the body. 3.41 meter per second. Alright. Okay. Determine the coefficient of dynamic friction between the stone and the ice during the last 14 seconds of the stone motion. So because you can see during the last 14 seconds, during this, well, let me change the color. During this part, this time interval, which is actually 17.5 minus 3.5, which is 14 seconds. During this time, the body is actually decelerating, right? There is a deceleration occurring here because the velocity is decreasing at a constant rate, so deceleration is constant until the final velocity is 0. Whereas the initial velocity here is equals to the maximum velocity that the body had, which is 3.41 meter per second. Okay, so why is it decelerating? It's decelerating because there is a friction force acting in the opposite direction of the motion. So the friction is causing the deceleration. We need to find the coefficient of dynamic friction. So what is the equation for the coefficient of dynamic friction? So we go back to the data block. So mu of s is static friction. So this is the coefficient of static friction. S for static, D for dynamic. So dynamic means when the body is moving, and static means when the body is stationary, not moving. So we will use this equation. I will explain what each quantity means there. So the equation, copying from the data booklet, is actually frictional force equals to coefficient of dynamic friction times R. Now this R is the reaction force, normal reaction force from the ground. So imagine if this is the body, right? This is the body, and this body has a weight W, which is equals to mg. Now the reaction force is actually counteracting this weight. Yes, so the normal means it has to be like perpendicular with the plane. So this reaction has to be equal to the weight, which is also equals to mg. So normal reaction force from the ground. So it actually obeys Newton's third law. For every reaction, there is equal reaction and opposite in direction. And the body is also moving with some initial velocity. So initially the body had a velocity of 3.41 meter per second, and after about 14 seconds later, the body decelerates to final velocity of 0. Okay, why is it decelerating? It's decelerating because there is a frictional force. This is a frictional force. This is capital F of subscript F. So there's a frictional force that is opposing the direction of the motion. So this is the situation here. We need to find the coefficient of dynamic friction. Okay. Alright, so an equation that we know is the Newton's second law equation, force equals to ma. Alright, so there's a mass and there is deceleration in our case. So if we can find the deceleration from the graph, that deceleration is actually due to the frictional force. Okay, so let's see how to find the deceleration from the graph. So if we go back to the graph, this is a graph of speed versus time. So we are right now here. So in order to get acceleration, we have to go in the forward direction. So to go from velocity time graph to acceleration, you have to find the slope of the graph. So let's find the slope of this line. Now to find the slope of this line, you just need to do rise over run. So just make this triangle. Okay. So let me find the slope. Okay. So let me write it down. So the acceleration or the deceleration is actually equals to the slope. And to find the slope, you do rise over run. So if you look at the graph, how much is the rise? So this is a rise. This much is the rise. How much is the rise? So go from 0 to 3.41. So it's 3.41. And how much is the run? So this is the run. So the run is actually this 14 seconds. So it's 3.41 divided by 14. 3.41 divided by 40. Just leave the answer here, and also put a negative sign because it's deceleration and the slope is also negative. So it's a negative slope because it's like in that direction. It's negative slope. Alright, so this is our deceleration. The units are meter per second square if you want to know. So we can put that thing here, but before putting that thing here, let's try to create an equation for coefficient of dynamic friction. Okay. Now, in the next step, we know that force equals to ma. Deceleration is caused by the frictional force. And do we have any other equation for frictional force? Yes, this one. So the frictional force is also equals to mu, the coefficient of dynamic friction, times r. So why don't we can replace this by this equation. So we can actually put this equation into here. So let's do that. So this thing can be replaced by coefficient of dynamic friction times r. This one. And same as it equals to mass times acceleration. So just copy this thing down there. Alright? So just substituting this f into this f. And we need to make mu of d the subject because that is what we need to find. So mass times the deceleration divided by r. R is also a vector quantity. Maybe you can put an arrow there. Okay, so we don't know any information about the mass here. Well, we know what is a mass because the mass is given from the... No, there is no mass. This is a different problem. So we don't have any mass, so we have to get rid of this mass. How do we do that? We realize that the reaction force from the ground is equal to weight because the body is no longer moving in the vertical direction, it's just moving horizontally. So all vertical forces must balance out each other. So we can just put mass here as it is, the deceleration divided by r. R is equals to weight, and weight is equals to mg. So we can replace the reaction force by the weight. This mass and this mass cancels out. So it looks like in the end we will be left with acceleration and the gravity. So the deceleration that we found is here. So it's going to be 3.41 divided by 14 from here divided by g is 9.81. So it has a negative sign because it's deceleration, and also the gravity is also 9.81 because the gravity is also acting in the opposite direction. Just put a negative sign there. Yeah. So it's going to be 9.8, but negative 9.8. So it's just negative, just cancel out each other, and you can just hit the calculator. So if you hit the calculator, 3.41 divided by 14 and then divided by 9.81, it's going to be 0.025. Okay, 0.025. So it's 0.025. There are no units. So coefficient of dynamic friction has no units. Don't put any unit there, and just round up to 2 significant figure. Because at most we have 2 significant figure here. Okay, you can see mass cancels out, and we have. So actually, the negative, negative doesn't matter here because the coefficient is always a positive number. So we have a negative acceleration, and g is also negative because it's acting in the downward direction. Okay, good. The diagram shows the stone during its motion after release. So this is stone, direction of travel, there's ice. Label the diagram to show the forces acting on the stone. Your answer should include the name, the direction, and the point of application of each force. So as usual, so there is a weight which is acting downward, which is equals to mass times gravity. And because of this weight, there's a reaction force from the ground. And the reaction force is also equals to the weight, because the body is not moving vertically. Because the body is moving in the forward direction and there's a friction acting, so the friction must be in the opposite direction. So there's a friction force. Okay? Yeah, you can see there's a friction force acting opposite direction. Alright? Yeah. So just a thought, because you have to include the point of application. So just be careful with point of application. Is like the weight always acts from the center of the mass. So you can see this is a body and the approximate center point of the body is this one. So the weight always acts from the center point. Okay. The reaction force act at the point of contact. So this body is under contact with the ice at this point. You can see at this point. So you have to draw the reaction force starting from the point of contact, not from the middle. So I shouldn't have drawn this one from the middle. So actually, ignore this one. You should draw from the point of contact here, reaction force. And then the friction also acts at the point of contact, from the point of contact. So and just be careful with the point of application of the force. Okay, and then this is the friction force. Okay, yeah, 3 marks for 3 forces. The correct point of application, direction, name. Define internal energy. Question number 3. The internal energy is defined as the sum of the microscopic potential and kinetic energy of the particles. So potential energies of the particles and kinetic energy of the particles. So it is not for the bulk solid body. It is the sum of the microscopic kinetic and potential energies of the particles of the body. So the kinetic energy here depends directly on the temperature, absolute temperature in Kelvin of the particles, and the potential energy depends on the intermolecular forces of interaction between the particles, and as a result is directly proportional to the distance between the particles. Right, so kinetic energy depends on the temperature, absolute temperature of the particles, and potential energy depends on the average distance between the particles. Alright, so it is not for the bulk, it is for the particles. Yeah, so the mention of atoms, molecules, particles, energy, the sum of the kinetic and potential energy. Alright, so also this, let me write it as potential energy depends on intermolecular forces, and it is directly proportional to the distance between the particle, and kinetic energy is directly proportional to absolute temperature of the particles. Okay, the reason why potential energy is proportional to distance between the particles because there is always some sort of intermolecular forces of attraction and interaction between the particles. So in order to move the particles away from each other, you need to provide potential energy to increase the separation between them, to overcome these intermolecular forces of interaction. That's why potential energy increases with the increasing distance between the particles. Okay, and yeah, kinetic energy is directly proportional to absolute temperature because higher the temperature means higher the velocities of the particles. So this velocities of the particles increases, and this is the formula for the kinetic energy. So if the velocity increases, the average speed of the particles increases, then the overall kinetic energy will also increase. 0.26 moles of an ideal monatomic gas. Monatomic gas means gas that is made up of single particles. For example, all noble gases are monatomic gases. They exist as a single alone particles. So for example, you guys have seen oxygen, right? Oxygen is diatomic because it consists of two atoms covalently bonded together to make a molecule. So it's a diatomic molecule. It's not a monatomic. So monatomic is like fluorine gas that just exists alone. Fluorine gas. So it's trapped in a cylinder. The gas has a volume of 21 meter cube and a pressure of 1.4 pascal. State how the internal energy of an ideal gas differs from a real gas. So we have an ideal gas A, we have a real gas. So a real gas has potential energy, whereas ideal gas does not have potential energy. The reason is because the main assumption for an ideal gas is that there are no intermolecular forces of interaction. If there are no intermolecular forces of interaction, then there must be no potential energy, because potential energy is entirely due to the forces of interaction between the particles. Since it is assumed that it doesn't exist in ideal gas, hence there must be no potential energy. And also the internal energy is the sum of microscopic potential and kinetic energy of the particles. Potential plus kinetic energy of the particles. Now for our ideal gas, since there is no potential energy, hence the entire internal energy of an ideal gas is entirely due to the kinetic energy. Whereas for a real gas, the internal energy is as a result of the sum of potential energy and kinetic energy. Why potential energy exists in a real gas? Because in a real gas that exists in a physical form in our environment, there are always some intermolecular forces of interaction between the particles, hence there must always be some potential energy. So you can see this plus this gives a bigger value than just a single kinetic energy. Hence the internal energy is always bigger for real gas as compared to an ideal gas. Okay, because ideal gas only consists of kinetic energy, whereas real gas consists of both potential plus kinetic energy. So it's higher for real gases. Determine in Kelvin the temperature of the gas in the cylinder. So since the gas in the cylinder is an ideal gas, we can use the ideal gas equation. And the ideal gas equation from the topic 3 in the data booklet is given by PV equals to nRT. P is the pressure in Pascal, V is the volume in meter cube, N is the number of moles, R is the gas constant, which is given in the data booklet, which is around 8.31, I will show you, and T is the absolute temperature measured in Kelvin. We need to find the temperature, so make temperature the subject. So if you do that, so the temperature will be equals to PV equals to nR. Let's sub in all the values. So T is pressure, so how much is the pressure? So the pressure is 1.4 Pascal. V, so how much is the volume? Volume is 21 meter cube, already in SI unit. N is the number of moles, 0.46. And we have R, so R is the gas constant. Let me show you a way to find the value of R. So just scroll up the data booklet. So there it is, gas constant, which is R 8.31, okay, here. Okay, so it's 8.31. Okay, just hit the calculator. Whatever the answer is, it must be in Kelvin. Let's see what is the answer. So it's around 7.7 Kelvin. 7.7 Kelvin. Okay, good. Yeah, units are important, so make sure you put in Kelvin there. The kinetic theory of an ideal gas is one example of a scientific model. Identify 2 reasons why scientists find such model useful. Well, it's useful because it's easy to calculate, easy to model. It simplifies the physical model, because if it's a real gas, then it will be very difficult to model it. So if it's an ideal gas and using the kinetic theory of an ideal gas, we can get a simple equation of PV equals to nRT. So let's talk about how simple the life for a scientist becomes to analyze the result. So talk about simplicity. So as you can see here, it's easy to model, predict, hypothesize, to explain, help with understanding, help to visualize, and simplify, approximate, and simulate. Simulate means like approximating the result. Okay? So it helps in the simulation also. usefulness of this kinetic theory of ideal gases. So also remember this PV equals to nRT, it can only be used on ideal gas because it is clearly a simplified equation that can only be used on ideal gas provided it obeys kinetic theory model, which is like there are no intermolecular forces or interaction between the particles. Question number 5. Two microwave transmitters X and Y are placed 20 cm apart and are connected to the same source. A single receiver is placed 44 cm away and moves along a line AB that is parallel to the line joining X and Y. Okay. Maxima and minima of intensity are detected at several points along AB. Explain the formation of the intensity minima. So minima happens when the two coherent waves interfere and they combine destructively with each other. So the amplitude just cancel out each other, and as a result there's a destructive interference, and destructive interference happens when the two waves are 180-degree phase apart from each other. So imagine there's like one wave here that's probably going in the forward direction, and we also have another wave that is going in the other opposite direction but kind of coincide with this wave at 180-degree phase apart. So there's a phase difference of 180 degree, so that the amplitude of one wave cancels out with the amplitude of another wave. So hence there's a destructive interference happening here. So they just cancel out each other, as a result giving us zero wave, no intensity. So this is what destructive interference means. The amplitude just cancel out each other, so they destroy destructively. Okay. For 2 marks, you just need to explain that there's a destructive interference occurring. So minima means destructive interference, which means the two amplitudes just cancel out each other, and it occurs when the waves meet 180 degree out of phase. So the crust coincides with the trough of two waves. The crust of one wave coincides with the trough of another wave. This top part is the crust, the bottom part is the trough. Crust, trough coincide with each other and cancelling out the amplitudes. The distance between the central maxima and the first minima is 7.2. Calculate the wavelength of the microwave. Let me explain the detail here. So imagine this is the slit, having a slit width of maybe small d, and there's a wavelength that is being incident. So this is the wavelength, and as a result some diffraction occurs there, and this is the screen, and imagine this is the baseline, and on this screen we have fringes. Fringes are formed on the screen. So we have this bright spot that occurs in alternating order to the dark spots. The dark spots are where destructive interference occurs. So 1, 2, 3, so maybe one more here. So the red ones are where constructive interference occurs. Okay, the two amplitude they add up together because there's no phase difference between the two waves. The crust and the two crusts of the wave, both waves coincide with each other, hence the amplitude add up together. So between two maxima there is a minima. So the blue ones are minima, where we have destructive interference, and constructive and destructive interference always occur in alternating order. We should always start with constructive interference. You can see this one is always constructive interference. Okay. Yeah, because the two waves coming from here and here, they coincide at this point, and as a result they have same length. It's an isosceles triangle, hence the path difference between these two waves is 0. So the middle fringe is always constructive interference. The amplitude will always add up together. So we always get a maxima here. And because this is always maxima, hence it is irrelevant and not important for us at all, because it doesn't change in its position. It's always stay there. What is important for us is this distance. This is called central maxima. So the distance between this and this. This is called the central maxima. Okay, the distance between this maxima and this maxima is called the central maxima, and this distance is given by 2s. the distance between the central maxima, this one, and the first minima. So what he is talking about this distance. This to, alright, let me zoom in. Choose a different color also, maybe pink. So the distance between the central maxima and the first minima. Central maxima, so this one is the central maxima and this one is the first minima. This distance. This is the distance that what he is talking about. As you can see here, 7.2. So this distance is 7.2. Okay, this distance is 7.2. 7.2 centimeter. Okay, if this distance is 7.2 centimeter, then how much will be this distance? Will it be double than 7.2? Yeah. So it will be 2 times 7.2. And this distance is equals to s, because if the distance between the central maxima from here to here is 2s, then half of it will be equals to s. This half will be equals to s. And this half is actually double of this distance, what he is actually referring to. First minima and maxima, which is this. Okay, so if you're getting confused, let me zoom this part for you guys. So it's like so I'm drawing this one, right? And then just below it there is a minima. This is a minimum. Okay, so the distance between central maxima and a minima, this distance is 7.2. Okay, you can see this distance is 7.2. Alright, back to the question here. What does he want? Calculate the wavelength of the microwave. So if you go back from the data booklet, we will borrow the wave phenomena equation, which is this one. S equals to lambda capital D over small d. So it's S equals to lambda capital D over small d. This is the equation. Small d is here, lambda is there, and the distance between the screen and the slit is capital D. Okay, this is the screen on which maxima and minima fringes are created, formed. So we just need to find the wavelength. So make wavelength the subject. If you make wavelength the subject, just rearrange the equation. Small d goes up there, comes S d to capital D. Plug in all the numbers. So this S is equals to 2 times 7.2 centimeter. And small d is the distance between slit separation. So this d, how much is this slit separation? So if we go back, and then this is it, 12 centimeter is the slit separation. So it's 12 is still in centimeter, so this is 12 centimeter, 7.2 centimeter. So keep everything in centimeter. Your final result will also be in centimeter. Okay. How much is this capital D? Distance between the screen and the slit. Distance between the screen and the slit is 54 centimeter. So you can see everything is in centimeter already. So whatever the answer we get here, it will also be in centimeter. So no need to convert everything into meter. So he just hit the calculator. So if you hit the calculator, just this times this divided by 54, you will get 3.2 centimeter. Yeah, correct, to true significant figure. So don't exceed the maximum number of significant figure. You can see this maximum significant figure given to us is 2, so don't exceed the 2 significant figure. So the wavelength is 3.2 centimeter. Okay, zoom out if you want. Alright. Yeah, just be careful with this S. This S is twice 7.2. And this red and this red, this is the central maxima. This middle maxima is this useless for us because it's always stayed there. It doesn't move at all. Radio waves are emitted by a straight conducting rod antenna aerial. The plane of polarization of these waves is parallel to the transmitting antenna. Transmitting antenna, receiving antenna, and they are 56 kilometer distance apart. polarized radio wave. So polarized is already plane polarized. So we can use that polarization equation. I will show you where it is in the data booklet. And identical antenna is used for reception, suggests why the receiving antenna needs to be parallel to the transmitting antenna. Well, it needs to be parallel to the transmitting antenna. For example, if this is the transmitting antenna that is like that only allows vertical plane of polarization to pass through, then the plane of polarization of the wave and the antenna, they must be parallel to each other so that maximum intensity of the wave can pass through. If it is not parallel, for example, if the plane of polarization is vertical but our antenna is not parallel, it is inclined at a certain angle, then there will be some intensity blocked and only small amount of intensity will be allowed to pass through. So we don't want any intensity to be blocked by the antenna. We want antenna to receive, to transmit, or to allow maximum possible intensity to go through it. That's why it has to be parallel to the plane polarization of antenna. Okay, otherwise it will be blocked. Yeah, so the component of the polarized signal in the direction of the receiving antenna, it must be parallel. Why? So that maximum intensity can pass through it. Receiving antenna must be parallel to the plane of polarization for intensity to be maximum. Okay? Yeah. The receiving antenna becomes misaligned by 30 degrees to its original position. The power of the received signal in the new position is 12. So in the new position, which means the power of the received signal, the received signal means final intensity. Calculate the power that was received in the original position. So at the original position, you will have initial intensity. Right? So we need to find what is the initial intensity. We are already given the final intensity. So since the radio waves are already plane polarized, how do we know that? Because you can see from the previous part, plane polarized. If the wave is already polarized and it passes through a polarizer, which is in our case is the antenna inclined at a certain angle, we always use the plane polarized equation, which is this one. Final intensity equals to original intensity times cos squared of theta. So theta is the angle of polarization. Okay? So let's use that equation here. So final intensity equals to initial intensity times cos squared of theta. We need to find what is the original intensity. So calculate the power that was received in the original position. So original intensity, so make I naught, which is the original intensity of the subject, which is final intensity, divided by cos squared of theta. So the final intensity received at the antenna here is 12. You can see the power of the received signal, received intensity, or final intensity is 12 microwatt. So 12 microwatt, keep everything in micro so that your original intensity will also be in micro. And cos of, what is the angle? So it's 30 degree, and then take the square. Just be careful with this square. So this square can be interpreted as first take cos of 30 and then take the whole square. Okay, people do a lot of this mistake. First take cos of 30 and then take the whole square. And also make sure your calculator is in degree mode. So if you have the calculator, you will get the answer of 1.6 10 to the power negative 5. Actually, let's do that on our calculator. So it's 12 divided by bracket. So we have a bracket open. Cos, sorry, what? Cos of 30, bracket of close bracket, square. Yeah, 12 divided by cos of 30, then whole square. Present we have 16 microwatt. So it's going to be 16 microwatt. You can keep the answer as it is, or you can convert micro into this SI unit, which is -6. Micro means -6 watt. If you want to further convert it into standard scientific form, then you just move one decimal place backward. It becomes 1.6 times 10 to the power -7. Go backward 1 unit. Watt. Or you can just keep the answer as it is here. 16 microwatt is the original intensity that was incident on the received signal with passing through a polarizer at an angle of 30 degrees. Okay. Calculate the minimum time between the wave leaving the transmitting antenna and its reception. Minimum time. Wave. What type of wave is it? Electromagnetic wave. It's a radio wave, and radio wave as being part of electromagnetic wave means all electromagnetic wave travels at the speed of light. So the speed of a wave is equal to the speed of light, and the speed of light is 3 times 10 to the power of 8 meter per second. All electromagnetic wave travels at the same speed of light, which is 3 times 10 to the power of 8 meter per second. This one is also given in that approximate this number. Okay, and the speed of a wave is constant, so don't use any Slovak equation, just use simple speed equals to distance over time equation. This one. We need to find the time, so make time the subject, so time will be equals to S over V. So we already know that it's a radio wave, and radio wave is an electromagnetic wave, and all electromagnetic waves travel at a constant speed of light, which is 3 times 10 to the power of 8 meter per second. And how much is the distance between the transmitting and the reception? Let's go back. How much is this distance? So if we go back a little bit, so there is the distance between the transmission and reception is 56 kilometers. Yeah, here. So 56 kilometer is 56 times 10 to the power of 3 meter. This is in meter, this is in meter per second. Okay, so make sure that you respect these units. So convert kilometer into meter. So yeah, just hit the calculator. 56 times 10 to the power of 3, bracket close. So make sure you add this bracket and then this bracket. And when you hit the calculator, it will give you a very small number. The speed of the wave is quite high. 1.9 10 to the power of 4 seconds. 1.9 times 10 to the power of -4 second will be the answer to 2 significant figure, because the maximum number of significant figure here is 2. Okay, speed equals to distance over time, because the speed of the wave is constant. All electromagnetic wave travels at the same speed of light. Alright, question number 6. Please use radar to detect speeding cars. A police officer stands at the side of the road and points a radar device at an approaching car. The device emits microwave, so it emits electromagnetic wave, which reflects off the car and returns to the device. A change in frequency between the emitted and received microwave is measured at the radar device. The frequency change delta F is given by this equation. So change in frequency equals to 2 times original frequency times the velocity of the moving observer or the source divided by the speed of light, because we are dealing with microwaves, and microwaves are electromagnetic waves that travels at a constant speed of light, which is 3 times 10 to the power of 8 meter per second. Where F is the transmitter frequency, V is the speed of the car, so it looks like the car is the observer and is moving with some velocity, and C is the wave speed, which is equal to the speed of light because it's an electromagnetic wave. The following data are available: transmitter frequency and delta F and maximum speed allowed. Explain the reason for the frequency change. Now, why is there a delta F, a change in frequency? So why does the frequency change? So obviously the frequency changes because there's a Doppler effect. So you need to mention that there is a Doppler effect because there is a relative motion between the observer, which is the car, and the source, which is the radar gun. Right, so let's see what are the options. So you need to mention that there's a Doppler effect happening here because there is a relative motion between the source, which is the radar gun, and the observer, which is the car. And this relative motion between the observer and the source produces a change in wavelength that ultimately results in change in frequency. So what is going on here is, for example, if this is the observer and there is a source, right? There's a source and there's an observer. So when it moves, for example, if the body is no longer moving, then the wavefront will look something like this. But the moment when this observer starts to move, the wavefront, for example, if it moves in that direction, then the wavefront will change. So the wavelength will change. So like this. So you can see there's a change in the wavelength, right? So the wavelength becomes shorter here, the wavelength actually shrinks here, whereas the wavelength actually expands here. So this relative motion between the observer and the source produces a change in wavelength that produces a change in frequency. The reflected waves come from an approaching source, or the incident wave strikes an approaching observer. So because the observer is moving toward the source, there will be a because it's moving toward the source, there will be a decrease in wavelength. The wavelength will decrease. So we already know this equation V equals to lambda f. So this is the speed of the wave. In our case, it is constant, which is equals to the speed of the light. If the wavelength decreases because the observer is moving toward the source, then the frequency will increase in the same proportion to make sure that the product of wavelength and frequency gives a constant speed. So that is why we have an increase in frequency, because the source is moving toward the observer, the car is moving toward the source, which is the radar gun. Okay, so you can see this is the source here, and the source is producing a wave, and then there's an observer. Observer is moving toward the source. So there will be an increase in frequency. Okay, so mentioned Doppler's effect, mentioned there's a relative motion between the source, which is the radar gun, and the observer, which is the car, and this relative motion produces a change in wavelength that causes a change in frequency. Okay, and then there will be an increase in frequency because the observer is moving toward the source. Alright, so just mention these important points, at least 3 of them. Suggest why there is a factor of 2 in the frequency change equation. This equation. Well, there is a factor of 2 because the Doppler's effect happens 2 times. Since the Doppler's effect happens 2 times, there's a factor of 2. Why does it happen 2 times? So you can see, if you look at the second one, the reflected radar appears to come, the first one. The car is a moving observer, and then a moving source. So the Doppler's effect occurs twice. What does it mean? So imagine this is the source. So this is the radar gun. So the radar gun produces a microwave toward the car. So initially the radar gun is the source, right? So the radar gun is the source, and this source actually transmits microwave toward the observer, which is the car. And this car is the observer, and this observer is moving toward the source. So when the microwave hits the car, right? The microwave hits the car, there's one Doppler's effect. And a second Doppler's effect happens when there is a reflection from the car. So these microwave actually bounce back from the surface of the car, because the car is a solid body and the microwave gets reflected at the solid wall of the car. So there's a reflection of the microwave. So, but the problem is that this car is no longer stationary. This car, which is the observer, is also moving. So when the observer, upon which the wave is reflected back, also starts to move, there is a second Doppler's effect happening. So it's like the observer becomes the source of this microwave. So this microwave, which is as a result of reflection, it appears as if it is coming from a second source, which is the observer. But in reality, it is just a reflection, but it appears that it is coming from a second source, which is the observer. So that is why there are 2 Doppler's effects occurring. So one Doppler's effect is occurring because of this source, and a second Doppler's effect occurs because this observer is behaving like a source itself. The wave is being reflected back from it. So that is why we have this 2V. The reflected radar appears to come from a virtual image of the device traveling at 2V toward the observer. So you can see the car is moving, observer, and then a moving source. Okay, so it's an observer and a source at the same time. So double effect occurs twice. Determine whether the speed of the car is below the maximum speed allowed. Okay, so we have to use the equation, change in frequency equation provided to us, which is delta f equals to 2fv over z. So we have delta f equals to 2fv over z. This v, this is the velocity of the observer, the car. So we have to make this v the subject. So make this v the subject, which is going to be c times delta f divided by 2 times the original frequency. Just plug in all the numbers. C is the speed of the wave. In our case, it is the electromagnetic wave, microwave. So all electromagnetic waves travel at a constant speed of light, which is 3 times 10 to the power of 8 meter per second. And then we have a change in frequency divided by 2 times original frequency. So we just need to take these two values from the data available. So change in frequency is 9.5 kilohertz. So it's 9.5 kilohertz. Kilo is 10 to the power of 3 hertz, right? Just convert everything into a SI unit. And then the original frequency, which is F, which is the transmitter frequency F, which is 40 gigahertz. So the original frequency is 40 giga. Giga is 10 to the power of 9 hertz. Okay, now just hit the calculator. So make sure you put these brackets in a fraction form, and that will give you the answer in meter per second. Let's see how much is the answer. So if we use the calculator, we will get 36 meter per second. So after you hit the calculator, you should get 36 meter per second. So what is the maximum speed of the car? So the maximum allowable speed is 28. And you can see this 36. So our velocity is 36 meter per second, which is bigger than 28 meter per second. And this 28 meter per second is the maximum speed. So determine whether the speed of the car is below the maximum speed. No, it is above the maximum speed. It is above the maximum speed. Yeah, so the car is actually over speeding. It is exceeding the speed limit. Airports use radar to track the position of aircraft. The waves are reflected from the aircraft and detected by a large circular receiver. So circular receiver is like a circular aperture. The receiver must be able to resolve, so it's a problem of resolution, resolve the radar images of the two aircraft flying close to each other. The following data are available. So diameter of the circular radar receiver is d, so this is small d. The diameter of the circular aperture, wavelength of the radar, so we have the wavelength, and the distance of the two aircraft from the airport, so this is the capital D. Calculate the minimum distance between the two aircraft when their images are when the images can just be resolved. So just be resolved. Okay, in order to solve this problem, we have to divide this problem into two parts. So the first part will be on diffraction, and the second part will be on resolution. Okay, so it's like this. So imagine there's a circular aperture here. This is a circular aperture, and this circular aperture has a diameter of this small d. Okay, so let me divide this problem into two parts. This is one part, and this is the back side of the screen. So this is the screen here, and we have two aircraft. So one aircraft is there, another aircraft is there, and then both aircrafts are producing some light, and these lights are incident on the aperture. So this is aperture, like a lens. For example, the pupil of our eye is an aperture, dish is an aperture. Okay, and there's a distance between them here, and also this distance between the aircraft and the aperture is capital D. Okay, and the distance between the two aircraft, call it maybe 2s, call it like 2s. Yeah, so it's very similar to the diffraction problem that we have done in the past. Okay, so call this distance like 2s. Or you can say this is maxima, this is maxima. These two are like central maxima. Okay? Central maxima. Okay. Divide this problem into two parts. Here, so we have a right angle triangle. Call this angle the diffraction angle. So this is called the diffraction angle, this theta. And then these two aircraft, for example, if this is like A, this is B, these two aircraft produces an image on a sheet, the backside of the screen. So there's a camera has a backside, just like the retina of our eye is the backside of our eye where the image is actually projected and produced. So this B is actually produced here, and this image of this aircraft A is actually produced here. And call this the angle. This is the angle of resolution, RES, angle of resolution. And the angle of resolution is actually a property of the camera or the aperture itself, so it stays constant. It depends on the properties of the camera itself. Okay? Yeah. So this angle, this theta, this angle is actually, we are interested in this total angle. This total angle is theta, so the half of it will be like theta divided by 2. Okay, and this length, since the total length is 2s, the half of it will be just s. Okay, the half of it will be just s. So let's just talk about this triangle only. This triangle. Okay, so let's talk about this triangle only. So you can see this is a right angle triangle, and on this right angle triangle we can use apply secateurs rule. So we have hypotenuse, opposite, adjacent. So opposite over adjacent is tan of angle. So we have tan of this angle, which is like theta divided by 2. So tan of angle is adjacent, opposite over adjacent. So opposite is S, and adjacent is this distance, which is this capital D. Okay. So we have to make an assumption here. So assuming the angle of diffraction is small, like how small? Normally the angle of diffraction, if it's smaller than 5 degrees, then we can use this tan angle approximation. So we can say that tan of theta is approximately equals to theta. So we can use this approximation, okay? It's called tan angle approximation. Okay, so this tan of this total angle can be approximated as theta divided by 2 equals to S over D. Okay, using this tan angle approximation, provided the angle is small. We can always assume the angle is small. Now what we can do is we can multiply both sides by 2. So after multiplying both sides by 2, you can see we get, so just multiply both sides by 2. So multiply by 2, multiply by 2, this 2 and this 2 cancel out. So let me write down the equation here. So we will get angle of diffraction equals to 2s divided by d. Okay, this 2s is the distance between the two central maxima, which is actually the two aircraft. So this is the equation of diffraction that we should apply on this side at the aircraft. Okay, the angle of diffraction is equal to 2s over capital D. Okay. Now let's go back to the camera, the second part of the diagram. So this is where resolution is happening. So we have to find this theta of resolution. So this theta of resolution is equals to 1.22 lambda over d. So let me show you where this equation is come from. This equation actually comes from here. Theta equals to 1.22 lambda over b. Oh, this is b. Theta equals to 1.22 lambda over b. This equation. Let me change this thing to b. So this is b. This is also b. So this is b. B is the diameter of the aperture. Okay, diameter of the aperture. So this is b. So this is the angle of resolution. So the angle of resolution is constant. It depends on the property of the camera. So a fixed camera will have a fixed angle of resolution. Angle of resolution is the minimum angle that is required for the two images to be seen just separate. So there are actually three cases. So let me, so we have two angles, right? So we have one equation which is here, and we have a second equation that is here. So we have three cases. So let me actually summarize the three cases here. So case one. So case one is when the angle of diffraction, so this part, so this is the diffraction equation, and this is the resolution equation. So yeah, angle of diffraction, this theta, okay? T-res over capital. This is not given in the data, but this is you just need to remember, right? Just derive only once, then you remember this, that theta is just equals to this length, total length divided by this length, right? It's this divided by this. Remember it. So when the angle of diffraction, there are three possible cases. It's either the angle of diffraction is bigger than the angle of resolution. Case 2 is when the angle of diffraction is exactly equals to angle of diffraction is exactly equals to angle of resolution. Case 3 is when the angle of diffraction is smaller than angle of resolution. Okay, so here we have the diffraction versus resolution. So diffraction is the first part of the problem here, and the resolution is the second part of the problem. So the diffraction is from the aircraft, it can be anything else there that is emitting some light source, and it enters the camera. So from the camera, the resolution starts to take place. So resolution means the ability to distinguish between two different objects. So this case, when the angle of diffraction is bigger than the angle of resolution, the image on the screen will look something like this. So they will be seen separate. So this is the image that I'm talking about. So you can see B and A. So here you have the image produced on the screen. Image, okay? So you can see they can be seen as separate, hence they are resolved. Second case, when the angle of diffraction is equals to angle of resolution. Angle of resolution is a constant angle. So it is actually this angle that we are talking about. This is the angle of resolution. So case 2 is when they are exactly equal, the two images will be seen just overlapping. Just overlapping each other. So they're just about to overlap. So there's like an aperture here. Aperture here. Okay, I'm not going to draw too much here. Angle of resolution. So this is just resolved because you can see the two images are just about to overlap each other. Just about to overlap each other. Just resolved. Third case is when the angle of diffraction is smaller than the angle of resolution, and that is not good. So what's going to happen is, let me draw here. What's going to happen is the two images will actually overlap each other. So image B and image A. Resolution. Okay, so the theta resolution was there something. So you can see they're like overlapping each other. So this is the aperture. So not to resolve. Not resolve means their images are overlapping each other. Overlapping, just resolve means like images are just touching each other, just overlapping or just touching. And resolve means they can be seen as separate, distinguishable. Okay, three cases, remember this thing, right? So when the angle of diffraction is bigger than angle of resolution, it's good. The images can be seen as resolved, separate. When the angle of diffraction is exactly equal to angle of resolution, then the images are seen just resolved. They're about to overlap each other, just touching each other. When the angle of diffraction is bigger than smaller than angle of resolution, then it's not good. The two images are overlapping each other because they are smaller than the minimum possible angle required for the two images to be resolved. So the images will overlap each other and hence they will not be resolved. So where are we? We are just resolved. Just resolved. So we want the two images to be just resolved. Just resolved means it's a case 2 problem where the two images are just resolved, meaning they are just touching each other. Hence we have to make the angle of diffraction equals to angle of resolution. Okay, so we have to make the two angles equals. Just getting a little bit messier here. Let me use a different color. So what we have to do, we have to equate the two equations. So angle of diffraction has to be equals to angle of resolution. And the angle of diffraction is here, which is like 2s, distance between the two light source, divided by capital D, which is distance between the aperture and the light source, equals to angle of resolution, which is 1.22 lambda over diameter, which is B. Okay, what do we need to find? We need to calculate the minimum distance between the two aircraft. So he wants us to find the minimum distance between the two aircraft, which is this one, which is actually 2s, right? So we have to make this 2s the subject. So make 2s the subject, which is equals to 1.22 lambda capital D. This capital D can go up there, divided by B. Alright, now let's just plug in all the numbers into it. So I'm sure you have copied down everything. Is there any space here? No, there's no space. Alright, so how about this? I try to erase this frame. Okay. So separate this, erase this thing. Let's go back. Okay, so we need 1.22 lambda. How much is the wavelength? 2.5 centimeter. Let's just convert everything into SI unit. So lambda is 2.5 centimeter converted into meter by multiplying by 10 to the power negative 2. And capital D, so capital D comes there. It's barely a space here. Capital D is the distance between the aperture and the aircraft, this capital D. So this distance of the two aircraft from the airport. Yeah, you can see the aperture is at the airport, which is 31 kilometer. So I'm going to write it here. So it's like 31 kilometer. Kilometer is like 10 to the power 3. Okay, 31 times 10 to the power of 3. Convert kilometer into meter. Divided by B. B is the aperture diameter, which is 9.3 meter. So it's already in meter. So 9.3. That will give us 2s, and 2s happens to be the distance between the two aircraft. This and this. So the minimum distance between the two aircraft, which is actually equals to 2s. So just hit the calculator. So if you hit the calculator, Make sure you include all the brackets. So you can see you have a capital D here, 1.22 lambda over b. It will give you around 100 meter. Alright, so this is the distance between the two aircraft. Minimum distance between the two aircraft for the images to be just resolved. Alright, you can copy everything. So just one thing missing here, so separate. The images can be seen as separate. Okay, so it's case 2 problem. Just resolve means you have to equate this angle of diffraction equals to this angle of resolution. The angle of resolution is constant. It depends on the camera, so it's a property of the camera itself. And this equation is also given in the data booklet, but this one is not given in the data booklet. So I will say to remember this. Just drive it one time and then you will remember how to get this thing. So theta is like the distance, this distance divided by this one. Okay, so if you have this triangle, so these are two sources and there's a aperture here. So if you have this capital D and let this distance be 2s, then this angle theta, this angle of diffraction will be just this length 2s divided by 2. Easy to remember, right? Just remember this angle of diffraction. And when you say just resolve, just make them equal, equate them, and then make whatever the quantity you want to find the subject, and then plug in the numbers and then find the value. Okay, next question.